So welcome back to this second part of the afternoon, where we'll be looking into the future. And so I leave the stage to Ignacio, who will be chairing the roundtable.
What is he doing?
Panic attack.
Yeah.
We start now the second part of the afternoon on the second celebration with this special event. But before we really go into it, I think it's a pleasure to have with us Martin Bertoli, the EPFL president, who, I mean, as you have heard earlier in the week, not only CECAM is celebrating 50, also EPFL is celebrating 50. And this is really a nice coincidence. This is also a busy period for the EPFL with this celebration. So at the end, we could arrange that Martin could come this afternoon and also take an active part in this discussion. But before we get into that, I guess Martin has some welcoming words for us.
Yes, good afternoon. It's a great pleasure to be here for the 50th birthday of CECAM. And as Ignacio said, it happens to be also the 50th birthday of EPFL by coincidence, so that's great. That's 100 together. We are extremely happy, of course, to have CECAM here at EPFL, both as a hosting institution, but also because we are very active, of course, in that field of research with a number of people. At least one is on the panel here, Nicola Marzari, Ursula Rodriguez-Berger, and others are very active exactly in the field of atomic simulation. When I looked up, of course I know about CECAM and I had met people and so on, and so I had forgotten it was a French acronym. So it dates a little bit, right? Because that was a time when you would do mathematics in French, and that was just fine. In the meantime, I think we all do, math with computational means and in English, but that shouldn't stop us from saying that it's fantastic to be associated to CECAM in the 50th year of birthday. I hope you guys are happy at EPFL. I tried to get this out of Ignacio, except for the price of coffee in Switzerland, and I would say the quality of coffee if you come from Italy. I think it's great to have you on campus because we like to have centers like this also interact with the local community, and I think it's a vibrant community here, and so this is all for the good of both institutions. So happy birthday, and thank you very much to be here.
As I explained at the beginning of the conference, and as I think you have appreciated through these days, the objective of this meeting to celebrate these 50 years is precisely not really to focus on what CECAM has done in the past, but really looking what is ahead of us. And I think that the sessions, the plenaries and the parallel sessions have probably conveyed or help us to get these ideas or what are coming challenges. This special session is to try to step back, to get a little bit more of perspective and try to think in more general terms. This is more difficult, but that's why we have then brought here few outstanding experts and members of the community who can bring their views from different perspectives. So we have Silke Biermann from the École Polytechnique in Palaiseau, then Nicola Marzari, as Martin said, from here, from the EPFL, Elisa Molinari from the University of Modena, Michele Parinello from ETH, Zurich, Christoph Schutte from the SUSE Institute in Berlin, Matthias Treuer, who is now in Microsoft Way in USA. I don't know if I said this correctly. And also Martin, as an active scientist, and with the expertise and view from the EPFL, will also agree to stay and provide his views. So just as a short introduction, I remind you that, as I said, we want to approach these challenges in a broad context. I will list these general ideas of how we could shape this discussion at the end, but from the CECAM perspective, just to remind you that indeed we have kept from the beginning the idea of promoting cooperation and fostering fundamental research among scientific communities dedicated to computationally intensive methods and grand challenges. And I think that's a question of how we can keep on doing that. Currently, we do that by having a very broad program of workshops and tutorials all through Europe. And as we are experiencing this this week, CECAM has grown and since its beginning 50 years ago. And actually, if you think, if you look at the type of activities areas in which our activities take place, you can go from electronic structure, density functional theory to classical molecular dynamics and molecular quantum, also in classical Monte Carlo, also to first principle dynamics, and then going up to coarse grain simulation methods and multi-scale modeling. And also more recently, I would say that there has been obvious, as computational science evolves, bridges to other communities that are newer to CECAM, such as the computational fluid dynamics or the connections with systems biology, and also more recently with the big impact and the interest and the opening possibilities of data-driven science. As I say, these are just examples of that all along the time we have had workshops and schools that have helped to address these challenging problems. And as I said, if you look at the number of activities, especially this since CECAM came here in EPFL, we have been increasing the activities to something like 80 per year in all these areas, which is clearly a substantial increase. And I think this is a good sign of the role that CECAM keeps playing for the community. And I think that's also why it's, I mean, it has a leading role to the development of computational methods. It's a focal point for also fostering research projects, engaging the nodes more recently, also to expand the role of community in, speakers and policy makers, and also driving new initiatives. And we are trying to consolidate and extend the role of intermediary between academia and industry. All these are roles that we have been taking with time, broadening the role and the service that CECAM provides to the community. And as I said, I think that in this panel, I think it's a good time to use this hour and a half that we have ahead of us to reflect or to think about challenges ahead from a broad perspective. And I would say that we will obviously hear to the panelists and we can move in different directions, but we have identified like 3 different main areas where I think it's interesting to try to think about what is ahead of us. One about new challenges in the different scientific areas in which our panelists are experts, and there will be also time for you from the audience to also contribute if there are aspects that you want to bring. Then I think it's also very important, when Dan was talking about the history of CECAM, CECAM started because the existence of a supercomputing center in Orsay and the need to be next to it, how we interact with the hardware, with the tools to do our computations has changed completely. And I think it's important also to think nowadays or in the future how this computational landscape is changing and how we as a community and CECAM as an institution should also position in terms of understanding how we can benefit from how hardware exists, the existing hardware, and how it will evolve in the near future. Also, how do we work with the existence of very well-established community codes and the tension with respect to the algorithmic development, where CECAM has definitely played a major role historically. As I said, there are new challenges of how computation will interface with data-driven initiatives, or for example, how do we address the possibilities offered by artificial intelligence in general, or machine learning more specifically. We already heard a few examples of how this is rapidly developing. And in this context, I think it's also important, as I said, to reflect on what should be the role of CECAM. How should we consolidate what we have been doing in the past, and what are ways of expanding core program or identifying new ways in which it's possible to better serve the community. So I hope this will be a fruitful, open, and interesting discussion. In order to organize it, I've agreed with the panelists that they will make a short 5-minute presentation of some of, I guess, I mean, you cannot touch everything, what they think is relevant from their perspective. After that, we will open a round where the panelists, on views of what you have been expressing, you can contribute or build on each other's introductions. And we will then can come back, depending on how the discussion evolves, into some of these questions that I open. And then we will also open the round for the audience to contribute and participate in this discussion. So I hope this will be useful for everything and for everybody, and we will learn from each other. And we will start by the presentation from Silke. So just,
Yes, good evening, everybody. And so let me start by saying happy birthday to CECAM, and thanks to all the people who have been making this possible over the last 50 years. So now we shouldn't look back. We shouldn't look back to the successes. We should look into the future. The next 50 years, this is very difficult. So let's restrict it a little bit more modestly to what are questions in my field for the next, let's say, 10, 15 years timescale. My field, let me define it more narrowly as being a subfield of electronic structure theory, so correlated materials that we want to treat with electronic structure methods. Correlated materials, just in a one-sentence definition, I want to understand under those materials where we need methods keeping two particle interactions beyond a single particle approximation in a wide sense. Then this implies that lots of interesting materials, transition metal oxides, F-electron systems fall into this category, but also that we have to look at which quantities actually we're interested in. And in particular, a hallmark of the community is that particularly interesting quantities are quite generally excited states properties, spectroscopic properties. So I've flashed here the example of spectral functions, things that are calculated in that are measured in photoemission spectroscopy and that we want to calculate from first principles. And as you see here, this is a field where I would say over the last 20 years there has been a lot of progress. You see on the left-hand side a calculation from 20 years ago. We're calculating a spectral function for elemental manganese, 1 atom per unit cell. It was a major research project, a big part of a PhD thesis, and with relatively nasty precision and heavy calculations on a supercomputer. Nowadays, you find problems in that field that you can solve on your laptop and with much better accuracy for much more interesting materials, more modern materials. So I think there has been quite a lot of progress in the last 20 years, but still it's a field that is quite young. And I think compared to some fields that will be following, this is a field that is much younger than CECAM. So the early papers of combining electronic structure theory and many-body methods to calculate these things date from 97, 98. So it's really a subfield that emerged when CECAM was well underway already. So what are the challenges now that lie ahead in the field? And for this, I would like to ask the question, so what is our Citius, Altius, Fortius? What do we want to improve over the next 10 years, let's say? And of course, quicker is always an option, but we want to be also more versatile. We want to be more precise. We want to have access to more interesting materials, going away from the bulk ideal crystal calculation, going to calculations where you can take into account geometries, where you can take into account realistic materials with defects, where you want to, for example, simulate dopant or substitutions more realistically. you want to do so while at the same time further eliminating parameters in the theory, doing ab initio calculations. And a thing that is often overlooked is this is a field where finite temperature calculations are a very important hallmark, and some challenge consists in actually reaching low enough temperatures, paradoxically. Going to a more complete description, including more degrees of freedom, including, for example, lattice degrees of freedom. If we talk about the photo emission that I just showed you, including matrix element, this is another Cetius, Altius, Fortius. More properties, more probes. So the field started more or less around spectral properties and now is going more vividly into the direction of thermodynamic properties, more complicated correlation functions, situations where you could probe more realistically, experimental probes that would also possibly lead you out of equilibrium. So this is one of the, I think, big issues in the field, how to simulate this, how to include collective modes in the description. And of course, then there comes the computational aspect. We want to do so more efficiently, and we want to do so less painfully. What do I mean by this? Well, many of the communities that will come up later, I think, have their, in the meanwhile, quite standardized codes that you can take as a package, run, and use. In the electronic structure for correlated materials community, code packages are only starting to come up. There's nothing like a commercial LDA plus DMFT code, and we are slowly only approaching code packages that you could actually, without being already for a few years in the field, download and just use. So I think this is probably a feature of the field which is coming from this quite young nature of the field. At the same time, maybe we should also keep in mind that we should stay down to earth. We should try to keep to relatively simple benchmark systems before addressing very complicated materials that would require the knowledge of what we should have checked before. This is sometimes certainly also a thing to remember. And finally, it's a field which, of course, follows with a lot of interest developments in neighboring areas, for example, combining with machine learning, even though I think this is still a very, very recent development and there's few true applications touching and really combining correlated electron systems with machine learning developments. So let me come to the question that Ignacio raised, what should CECAM bring in? So from what I said, you probably deduce that the main first request of the community is probably not the big data-driven access and evolutions in that direction, but that there is also more basic requests, I would say. For us, it is important, I think, to strengthen the interface with the real world, talk to chemists, talk to experimentalists, talk to different communities, for example, from the machine learning side. Also check back with people coming from analytical approaches. So CECAM workshops being open to communities that can be brought in is, I think, an important issue for us. How could one strengthen interactions between communities? So I have been discussing a bit with colleagues in the last days, and there was the idea coming up, what would happen if it was possible, for example, to run 2 CECAM workshops in parallel? If there was the infrastructure to do that, you could have one machine learning workshop, one workshop on correlated electronic structure, and in that way you could probably foster interesting interactions, a little bit on the model of what people do at the KITP in Santa Barbara, where you bring together sometimes astrophysicists with condensed matter theory or things like this. And finally, maybe let me drop a last idea. CECAM is certainly an issue for the future. That means also for the young generation. All political parties have their young whatever. Why is there no young CECAM? Shouldn't there be some young CECAM group? having maybe also dedicated young researchers workshops and bringing the field forward. Let me put this as a question, and then I pass the command on to Nicola. Thank you very much.
Thank you very much. Nicola?
Great. Thank you, Silke. I stand, and I guess I'm actually painfully aware of what it means going through a 50th birthday. And so I'll use another 50th birthday that came up this year, so from 1969. And I like it because it's all about a moonshot, the importance of setting oneself goals that until recently you thought they weren't possible. Now, Dana was very elegant in his talk, and somehow he says, I won't go down to say actually what the numbers are, but I actually had the numbers here because I think sometimes it's good to take, a faraway vision, exactly as we are doing in this picture. And so I put down here numbers for, funding in major areas in the physical sciences. So going from the European Space Agency, 6.3 billion. I'm using Swiss francs, or dollars is the same per year. ITER in Carandash, around 1.8 billion francs per year. CERN, 1.4 billions. Major facility, 0.4 or 0.3 billion for some of these large synchrotron free electron laser and so on. So this is, infrastructure, let's say, in the physical sciences. Let's look at a few more numbers and data, and this is a slide that I use with our friends at APS. This is actually the list of the most cited ever papers in the journals of the American Physical Society. That's where you find the gravitational waves, where you find cold atoms. And the ones in red are about electronic structure simulations. So the top 15 and 18 out of the top 20 papers in 120 years are about exactly this field. And if we widen a little bit the perspective, so not only physical sciences, all of the sciences, engineering, humanities, medicine. Well, Nature did this work in 2014, looking at the most cited papers ever. And in particular, they analyzed the top 100 papers. And actually, the field that was most represented in that top 100 slice was actually density functional theory. 2 papers in the top 10 and 12 papers in the top 100. So this is actually the impact that this field is having. And this is because some of the ideas that have been mentioned before, because we have better and better algorithms, we have novel theoretical ideas, and also at the end of the day, even if we don't have new ideas, we sit on this very comfortable paradigm. Actually, the numbers just for classical digital computing are that throughput capacity has been doubling every 14 months. So I gave this talk to 30 Wall Street billionaires, and they were getting bored about materials. And then I told them 100% growth every 14 months, and they all came awake. And as I said, this is just with classical digital computing, maybe neuromorphic computing, maybe qubits will be in. And so, one of the statements that, we keep saying, but should be very clear when you sort of, think at this, semi-logarithmic straight line, is that 21st century science and discovery will be actually driven by computational science. So the goal is not, understanding this, but deciding what we are doing about this. And the answer is that we are actually doing very little. And to celebrate, the 50 here, I have this movie that I love. These are the Rocketdyne F1 engines. So this is Saturn V, 12,000 kilos per second of liquid oxygen and rocket fuel. Okay, the hardware is gone. Rocketdyne has disappeared in the 70s, so we don't have anymore the hardware that brought us to the moon, but we actually have the software. You go to GitHub and you can download the entire source code of Colossus. This was the first ever, silicon integrated technology, and that was what was driving Apollo. So software, not only sort of, has a much longer life than hardware, but is what is driving not only our science, but the science that we will be doing. And these are examples from projects that are very dear to me, where we contribute or we even created. And these are the number of papers that some of these, I call them software installations, exactly as you think at a major facility, at a hardware installation, they produce. I mean, Dan said 1,400 papers per year with CERN. Well, Quantum Espresso, 2,800 papers per year, doubly exactly. So you see, this is really, serving and empowering an entire and very large community. So these are my conclusion, because I think the solution is unbelievably simple and in front of us. So the first statement that I've already told you is that computational science will be straight at the center of innovation and discovery in 21st century. It has a completely different scaling model compared to physical infrastructure. Most of it is actually not only open and shared, but is redeployable anywhere at zero cost. And that is what is unbelievable to me. If you want to get a second synchrotron because you have to serve double your users, you have to build a second infrastructure. With scientific software, you don't have to do anything. And notwithstanding this, and notwithstanding all the benefit that comes from this, we are not investing. And we have said this for many times. Why are not investing in structural long-term way, in ways that can really lead to the development of scientific software as we should? I've been thinking of this, and I realized, this morning that actually the solution is simple and is in front of us. We have a CECAM, and I think my suggestion is that, this should be, an ambitious long-term project, having an institute that is funded by state members, but not with, the current funding, but, for me, 100 times more funding, 10 times more funding. Here is where we have to have the professional, long-term staff scientists and career that do for scientific software what is done by hardware research installation worldwide. Okay, thanks a lot. End of the preaching.
Thank you very much, Nicola. Now, Elisa.
Yeah, actually, I was going somewhat along similar lines as in the previous talks, but I'd just like to continue a bit on the community pride and actually ask the question, how comes that after all our codes, the European codes, are probably, I think they're recognized as leading somehow worldwide. They are, I don't have the detail data, actually I have them, but I don't think it's worth playing this supremacy game. But it's true that we have some of our codes, and many of the developers are here around, from molecular dynamics to electronic structure. They are really lead codes that are leading worldwide. And even when there are codes and communities in other countries, we see here many of the people were educated in Europe and contribute from a European background. And I think that's not so obvious and probably not so clearly recognized, although I know that in some of the policy debates in other continents, people are asking how comes. So I think it's an interesting question, and somehow, well, before coming to the how comes and how we can keep it going, I think we should realize that this was not so obviously clear in our funding schemes until very recently. So until not long ago, I have been hiding anything that was related in my group to developing something about the codes. It was hiding in proposals that had nothing to do with codes and with method developed. It was only a few fortunate groups that could maybe get that. We were basically submitting a proposal on simulating some photovoltaic process or some photosynthetic process or anything like that. And then hiding in there was that with the overheads we would contribute to the development of the codes. And was true for many of us. So now I think people are starting to realize that there is a value in the codes that we produce, and especially so for some more important groups that are doing that. And this is happening for a number of reasons that are at the same time an opportunity and a challenge. One reason is that we are back into a time where code development and workflow development, the whole process of codes, has again very much to do with the development of the hardware. So it's not so general purpose hardware is less so right now, and I think if we want to continue with a pace like the one that was mentioned before, we have to think that we really have to design or redesign our codes together with the development of the hardware. And sometimes it's not so much hardware that is developed for us. It's very often hardware that is, for scientific computing. It's very often hardware that is developed for video games or for completely different applications, but we need to play together with the hardware developers in order to gain from this process. And that's, in a way, at the same time makes our codes very valuable, because interacting and knowing what is needed from the side of applications is also becoming important in the hardware development. So that's one component. And the other component is that the culture that in a way is embedded in terms of algorithm development and code development in this community is really amazing, an invaluable culture. And it's something that is deeply different from pure computer science. It is computational science, and I think this interplay can be very valuable and is now being very much recognized. So there's a number of successes and of reasons for pride. At the same time, there's a number of challenges that come from this. So one thing is codes are becoming somehow more, at least in some sectors, maybe not all, push-button objects, and that is can be very dangerous. And especially, I think we need, as a community, to be much more aware than we are of what this can imply. So, in a way, I think having published results that do not contain information about the codes that were used, about the conditions in which how the calculations were performed, where the data are available, in short, that are not reproducible. This is something that is happening more and more, and I think we as a community, and CECAM could help us in calling the attention to this. From ourselves in the community, those who are refereeing, but also very much from the journals, we should help building up a policy that in a way avoids the bad consequence of this process. So on one side, it's trying to avoid bad misuse of this process of codes becoming such an important value. The other thing is, how can we make sure that the type of development that is needed now is sustainable from the people of our community? So I think, Silke, it was interesting what you're saying about young people, but if we're going in that direction, and so much value in the codes, and we need people who are scientists, computational scientists, and at the same time spend a lot of their work on codes. What are the careers that these people can find? Are our departments ready to recognize the work that is embedded there? Are we able to have people who we have heard here talking in our sessions are very often very well recognized, but there's a real difficulty in many countries in seeing recognition to for young people who are investing in there. So I think we need a collective effort in building careers and building ways of having all this recognized. Somebody who builds a key component of a very important code is very often less recognized than somebody who runs in an automatic way, some push-button operation in a code, and that's something we need to work on collectively. I have one more lateral comment, and I keep some of the rest for maybe a next round, as to how comes that this community has developed such, and we've been all together so successful collectively, also on the code side and on the computational physics and chemistry side. My impression, and maybe I have a bias from the Italian perspective, my impression is that part of this is because this community, including CECAM, has been able to accept emergent phenomena in a way that was not too rigid, and that we didn't get such strong powers opposing this emerging dynamic phenomena. In Italy, that I would say that's for sure. I mean, the mess has some advantages, and if there are so many Italian contributors to the system, it's because I think we have a very solid fundamental education in basic sciences, and not leaning immediately towards engineering and so on, maybe. But I would say there is one component of allowing some emergent, at least in somewhere, behaviors that are not too much in the heart. So I know countries where computational sciences were kind of second-hand, not really, no real physics, no real theory. I know countries where, I mean, you had to fight in order to find a place for this. My impression is that CECAM has been a place which was not just defined as an easy place for a small community. It was also a place where flexibility and emergent phenomena could come up, and I'm very grateful to that, and I think we should make an effort to design the next 50 years in such a way that this is still possible.
Thank you very much. Michele?
Okay, I am the oldest one in the panel, not the oldest one in the audience. Luckily, there's someone who has the banner. But I would start my thing by going back to being old. I remember the time in which you punched cards to make your program and so on. But also, I recall the days in which those years at the beginning of CECAM, where people would come here, talk to each other, exchange code, learn from one another, and making friends. So I think one of the reasons why Europe, in my opinion, why Europe is so competitive is because it was forged this community. I mean, I met Dan Frankel, Jean-Paul Ricard, Giovanni, and so on. All the people of that generation knew each other through Gianni Iacucci, through CECAM. And I think that was a thing of invaluable thing. And I think this ability of creating and maintaining a community should be preserved as much as possible. That's the added value of CECAM. That should not be. The other important things of those days was that we had some personality which were really outstanding. As many of you know, I have a great admiration for Anis Rahman, and he was a model of integrity, honesty, that we should keep to maintain. So in terms of reproducibility, you were talking, I remember what he did in those days. There was not possible to store many data, and so on. He had the output of all his runs, big piles, okay, and he was able to trace calculation after calculation where the data came, which program generated them, and he was at any moment able to reproduce his data to the last digital figure. It's something quite amazing that is very, very difficult to do. So I think one of the role of CECAM should be to move in this direction. So have a place where, as Elisa was saying, where you store your data, where you put the program, so that anybody and everybody can repeat your calculation. In our community, we are trying to do that. There is an initiative which is called Bloom Nest, a depository, and also I think a similar initiative are flourishing, and this should be encouraged because its reproducibility is one of the key scientific point of view. I like the Olympic thing, Citius, Celsius, and so on. I would add to that various issues, intelligentius. So in the sense, not in terms of smart, I don't know enough Latin, actually, I forgot Latin, in spite of having studied for 8 years, but I essentially forgot most of it, sorry. And I don't do experiment anyway. Okay, thank you. So where was I? I'm an old man, guys. Huh? What? Intelligent. Intelligent, yes, because especially in the time where you push a button and you get a result, I don't think there is much value in result where you don't understand what goes on. If you can make a model out of it and learn from these things, new things, and allow help, I think at the end of the day, what we need to do, and it should be our job, to come up with a model. Numbers are important, but understanding is also very important and more important. Okay, so that's the relevance of having public code should not be underestimated, and I would agree that the CECAM should be one of the missions to foster this activity, which is so successful in Europe, I must say. Okay, so a few more things. I mean, if we look at challenges, I don't want to go through many things because I don't think that's the point. But one thing that I would like to see growing is what I call non-local chemistry. So the traditional vision of chemistry, chemical reaction, was something very localized. You have this bond or that bond and so on. But actually, real-life chemistry, if you look at real catalytic process in the industry, are so enormously complicated, and that cannot be understood. There must be a more global description of the thing. Temperature has to come into place, and the effect of temperature can be very dramatic. I bear in mind some of the beautiful calculations that Julia Gall has done that clearly show that if you take a frozen configuration and don't include temperature, you get it simply all wrong. So that's something that I wanted to say. Another point in which CECAM should play a role, should be teach us to interface what we do with the public. And so that Dan was saying, the public recognition of what we do is really minimal. And instead, some of the things that happens in our community are of great relevance. We have to learn to sell ourselves. And okay, so that's for a few disordered thought. Okay, another thing I want to add is the issue of machine learning, artificial intelligence. They are with us, and I think they are with us to stay. And the students of tomorrow or the present will have to have in their CV machine learning, like we used to have a differential equation and integrals and so on. That's a tool which we have to promote, because that's really powerful, and to stay outside of that would be foolish. Okay, so these are the ramblings of an old man, and I would...
Yes, I think these are good thoughts to start, so
yeah,
thank you very much. Move to Christoph.
So in some sense, I now, after these four speakers, can only repeat things that already have been said. What I wanted to say was that if we think about challenges, then the field has impact, and there's a lot of good science going on. But the awareness on the and recognition on the political and society at large level is not so great. And this perhaps may not be a main problem, but with the new developments in the direction of data sciences, not only machine learning, but data sciences, big data, artificial intelligence, whatever you want to call it, deep learning, there's a wave of things coming where computers are used for other purposes than doing computations or scientific computations. And this gets so much awareness also for the young generation that we have to be careful to get our share of the good talents, because many people just want to go into these fields and develop them further. And I also believe that these fields will stay. Many think it's a hype and it will go away after 3 years. I don't think so. I don't think that this will stay. And but this is a challenge, but also an opportunity, because of the following things. One aspect is that if we think about what, for example, deep learning is doing, then learning always is a kind of iteration, and often it's an iteration of trying to find something on a complex landscape. It's finding a minimum in many cases. And many things these people are developing at the moment have already been developed in a different context in our community. And so we have an opportunity. We can go into these fields and change things and perhaps even conquer parts of this development. And I believe that we should do it, and we should do it quickly. But that's a community effort. It doesn't happen if a few of us publish some papers about it, especially not about using machine learning for doing our stuff. Because there are also papers outside. One in the math world, there is an article called Deep Trouble, which more or less tells about that mathematics, analysis, and also computations in our thinking based on physics, first principles, will simply be marginalized, because many of these things can be done with other means, which perhaps may be possible in certain aspects. So we should be part of it, and we have the power and also the capacities and the knowledge to do that. Which means take our stuff and use it there, and perhaps make a field out of it, which is a field where not only computational means of our structures are used for molecules or atoms or materials or whatever, but also for understanding neural networks and their dynamical behavior. And that's a huge field. And what is sure is that data science or computation or computer science, that's a dark power. It will strike back. The empire will strike back. So the only hope that I have in some sense is that theory or mathematics may be with us in this fight, and that at the end we are successful in getting parts of this into our discipline, merging it. So we are heavy on the model-based side. All the stuff about artificial intelligence is heavy on the data-based side, and there must be a union of it. And if we get a part of this under, I don't like to say this, but under our control, doing it in this community, we will definitely have an opportunity there. And we should use this. Thanks.
Okay, thank you very much. Matthias, yeah.
Thank you. Yeah, so when I was invited here, I was still part-time at the ETH in Zurich. Now I'm full-time at Microsoft. The one Microsoft way actually is just the street address. So I just work for Microsoft. And I work in the hardware division. We're building cloud computing hardware. So why would an IT company like Microsoft that was known for software, why would they want to hire somebody like me? Why would we be interested now in CECAM? And the reason is simple, that as was alluded to before, in order to really make progress in computing in general, we need better software, but we also need better hardware. And so we have to develop and build the better hardware. And the reason why Microsoft hired me initially was to build up a team to simulate materials, to simulate devices for building quantum hardware. And that I built up, but as I did that, I realized there's actually much more. Because the question then comes, what if we build new hardware, what would we use it for? And what will we use the quantum hardware for? And thinking through that, I realized that really the big killer app is simulations of quantum systems. That's really where it will shine. And so then we started to think about kind of what are the problems that we could solve, the problems that we cannot do on classical hardware or that are super hard, but where quantum hardware will really be a game changer. And the mission of the team is basically to build and deploy a quantum system to solve today's unsolvable problems. But then I argue that actually we should broaden it. We don't have to wait for the time when we have a large quantum system, but if we are a company that builds up the world's leading hardware, that grows 70% every year in the cloud area, then I want to use the capabilities we have already today to solve problems that seem so far hard for us, infeasible. And so there is a chance to use all of the capabilities offered by cloud computing, also so in this field. We have hardware where that includes supercomputers, GPUs, FPGAs, now so that you can build your own accelerator. But more even, there is then the software to scale out, to go to massive scale, high throughput, and with it, all of the tools developed, as mentioned, to do the data analytics, and all the tools the company built for machine learning. I think there's a great opportunity here to combine the general compute capabilities built up in the industry, the tools built up for MLs, the tools build up to massive computations with the software done by researchers here to solve problems that we can't solve alone. So you don't have to influence the dark side to whether they can be manipulated to help, but the tools are out there, they are there, and they can just be used. And so I see an opportunity to jointly solve problems that are so far unsolvable and make real progress.
So come to Martin. So
thank you very much. First, it's a great honor here to be on the panel. When Ignacio invited me, he said, there are a bunch of outstanding scientists. Actually, I know most of them, and I know how good they are. So, you know, to balance the panel, we wanted an administrator, which is sort of a mild form of an insult. And so, so I come as an administrator who actually has programmed with punch cards, so I'm of the wrong generation on top of it, so not only an administrator. But let me give you just an anecdote to start, and then I have a few points to make, because I'm sort of agnostic, you know, about computer science, data science, model-based, data-based, and so on, because I'm paid to be agnostic and to sort of try to look at the big picture. I'll see if I manage to do it. So the other day we had a review of a paper on you know, one form of Euclidean distance matrices, and so you said, oh, you know, what you have might be interesting, but why didn't you look at molecular conformation, which is not at all my field. We do inverse problems, signal processing, and so on. And so he said, oh, let's look at molecular conformation. You know, we had this method where you would use torque angles, van der Waals distances, and Euclidean distances. And so the PhD student, you know, goes there, you know, works out the algorithm, looks at synthetic data, you know, gets interesting results. Okay, so she was very happy. And then she says, well, if I want to publish, I need to compare it to somebody else's result, right? So she goes to the literature. I mean, it's very fresh. It's from about 10 days ago, so I have to trust her. I didn't do, you know, my own search of the literature. She comes back and she says, this is amazing, because the people that work on molecular conformation, I don't know these people, they might be in the room, so I have to be careful. You know, they publish papers and they say, you know, the algorithm is you do this and that and so on, and here is a picture of the result, okay? So there was no code, no data, no nothing. Okay, and she, you know, we have in the lab a tradition of reproducible research. So we publish the code, we publish the data, of course we write the paper, we put the theorems, and you know, she was all upset. I said, this is a fantastic opportunity, right? Because if you indeed have a good algorithm, which I hope she has, you know, it will become very popular, because this entire other community is sort of doing dark magic. Okay. But I also should say I was extremely disappointed that the community that works on an extremely important problem would not have the discipline, the self-discipline of reproducible research. And you know, before this job, I had another administrative job. I was at the National Science Foundation in Switzerland, and I sort of saw all these communities, and different communities have different levels of sophistications with respect to reproducible research, publishing data, you know, sharing results, etc. You know, so biologists, I don't think there are too many biologists here, keep everything under the table, right? Because they are so scared that, you know, somebody will steal this great idea and publish in Nature or Science before them. You know, mathematicians are on archive, right, with the conjecture, and, you know, 300 years later, you prove Fermat's conjecture. So, you know, this is very different communities, right? I think there is only one way to do science. It's to do reproducible science. Ultimately, this is, this way of doing things will overcome. But it's a long way. I was very disappointed when I looked at various communities. So let me make a few comments. At EPFL, what we have introduced is actually not computer science for everybody or programming or God knows what. We have introduced something we call computational thinking, which is neither computational science nor computer science. I'm sorry for both sides of the dark side here. Computational thinking is, learning to the students, teaching them how you can pose problems that, in addition to math and physics, which I see as, a way of formulating problems so you know when you know, physics, formulating problems so you can approximate them. Computational thinking is formulating problems so you can use a computational means to find a solution. That might be a computer, that might be a neural network, it might be a quantum computer in the future. But this is really what we have to teach the kids, right? Of course, for you it's obvious, but this is not obvious when you have, engineers, architects, all sorts of scientists and so on. So we are in a total reform actually of the curriculum at EPFL so that everybody on campus has a track on computational thinking from day one, and it will actually branch out into specialization, computational chemistry, machine learning, etc. Good. Then there is a question of machine learning versus artificial intelligence. The only thing I'm going to say is that machine learning is written in Python and artificial intelligence goes into PowerPoint, okay? And that's the difference. Supercomputing versus cloud computing, that's another favorite one, right? So, the physicists think, if you give me a supercomputer, I'll give you the answer. And then you go to computer scientists, they say, give me a cloud computing infrastructure, I'll invent PageRank or something, right? So here again, it's not so clear. It depends on the problem. There are problems that are very well solved on supercomputers. There are problems that are very, very well solved on totally distributed systems. Depends on the question, okay? Data science is here to stay. Actually, science, okay, unless, except logic and, maybe topology, most of science is actually data science, even if it's not told like this, right? You look at chemistry at the end, you want to publish a paper, right? You don't send, little vials around the world, right? And so it's about gathering data and extracting knowledge from data. Now, this is extremely powerful because all the experiments I can think of end up being, digitized with data being analyzed by computational means, okay? And if you look at another favorite of mine is protein folding, right? So a gazillion people work on protein folding, 30 years of research, great papers, great results, and so on. And you have a little startup in London called DeepMind that says, maybe we could think about, protein folding. Now, what's interesting in the DeepMind endeavor is that it's not a bunch of computer scientists that did this, okay? So they did an interdisciplinary team where you had physicists, biologists, chemists, computer scientists, applied math people, and so on, okay? And in, I think, 18 months, they came up with something called AlphaFold, I believe, you must know the story, went to the, yearly competition of people, the Olympics of protein folding, and essentially beats the rest of the competition, out of the dust. There is something to be learned there. Don't underestimate the power of machine learning. That's one. At the same time, these people needed the help of all the people they could get. Because if you put a bunch of computer scientists to do protein folding, the first thing that happens is a computer scientist will say, this is a boring problem. We want to solve, P is equal to NP or something, that excites computer scientists. They're not going to solve protein folding. You only solve protein folding if you have domain specialists coming and saying, this is really important because it's going to change the face of biology. And you need physicists and you need, mathematicians, etc. And so I think you as a community have a very key role to play because you have extremely strong methods. And you should just go out there and apply the methods to all these other great problems that exist, are just waiting to be solved. And not think, that some AI people will solve it. It's not going to happen. You need real specialists together with domain scientists to actually solve these problems. And so with this, I would like to say that I think there is a great future for CECAM, right? Because you do computational science at the highest possible level. I'm very happy that Europe is leading this field, okay? At the same time, I think it's extremely important that you work with open source software. My favorite example is from another field, is that NMR is very often used in neuroscience and neuropsychology to find sort of correlations between, if you think of this, that other part of the brain lights up. Well, it was used, finding correlations in MR data used a commercial software. I think about 15,000 papers had been written, published, based on the commercial software, when it was found that actually the statistics were wrong, okay? I kid you not, right? So potentially, these 15,000 papers, God knows which results were correct or not. So again, it's a discipline, it's a science discipline. Software, like math, has to be reproducible. We have to see how it is written. It is not possible that we do science with proprietary software. Sorry for Microsoft. And so, it's a whole movement about Python notebooks, about, really documenting completely how science is done, I think is fundamental to the endeavor of science. And so I wish you a great, continuation of 50 years of success.
Okay, so I think thank you for the different contributions. I think I've kept in line with previous chair people to manage not to keep time. But I think we still have a bit of time for a more open discussion. So there are quite a number of issues that have come out. I would say, I don't know if some of you want to come back to other points that have been raised or open it directly to the audience.
I would hear from you.
Yeah.
I have one reply. That is, if you go to the microsoft.com/quantum webpage, you will see that all the software we have in quantum computing is open source. The compilers, the libraries, the samples, everything can just be downloaded there.
Fabulous. Okay, thank you.
Because it's important.
Yes. Okay. So we agree.
Okay.
Build a workforce, show what one has done, share the codes and knowledge.
Yeah.
Okay, so then maybe we can open to questions that may be coming from the audience. So Dan, so wait for the microphone. So that, yeah. Yes. It's off.
That was
Now,
it.
now
Okay.
it's
Now,
yes.
first of all, I very much enjoyed the presentations of the different panel members. But I one question that basically Dr. Vetterli addressed a bit, but I think is really key, is that we talk about the huge increase in computing power, but we should also take into account that experiments have had the high throughput experiments are completely changing the way data are being generated. You can't just take, like in the past, you took 10 points or 100 points, make a plot compared with theory, say, oh, this is great or not. Now you talk about billion of data points, and it really changes the way you do science. And I think that it means that computing will be much more integrated with data science. Yes. And just to take a few examples, because there's been a bit of a focus on how the existing techniques will survive in the future. But because what Nicolas said, computing, the developing of the computing power drives that the development that everything will be computerized in a sense. So there will be systems that we can't even dream of addressing right now. Like, for instance, the organization of complex living systems, the microbiome, you mentioned it, and it will not be done without the tools. First, the computing tools, the machine learning, but also, I would say, the techniques of, say, statistical physics, to simply know what it all means, and to, in the end, bring it back to simple concept, because in the end, computing is never an aim in itself. We want to understand things, and I would very much like to know what panel members have to comment on this.
Yeah, Elisa?
Yeah, I think it's I don't know if it's my turn to, I don't want to answer, but just to comment. I think this is a very important point. And it has different aspects. One is if you happen to go around large-scale facilities now, there's people building beamlines where synthesis is automatized and experiments are made automatized and so on. So in a way, it's just a lot of data coming out of experiments similar to the ones that we have been familiar with. On the other hand, it's also in completely new classes of experiments, time-resolved experiments. Just think of free electron lasers and so on. So new classes of experiments where the dynamics and the out of equilibrium phenomena become more important. And then there is also this being pervasive throughout, sensing everything. So there's really a lot of aspects where this is not so far in a dream, is really happening, and the data, the beamlines are going to be ready in a year or two. So that's, and there's complete new fields where they're planning to look in a very systematic way from, I don't know, batteries to photosynthesis and so on. This is all thought in terms of a complete cycle where theory is integrated. Now, this brings in a number of issues related to data from the experiments, how they are managed, and also how they can be somehow compared with what we are doing. Just giving names to things in an automated way. This is, I mean, there's whole teams working on this, but I think we should be aware that this must involve our communities, otherwise we are completely out of the process. And if these ontologies are defined in different ways, and not bottom-up on the experiments, and not bottom-up from what our communities may find important, then we won't be able to interact with that whole world. So that's one aspect. Another aspect which I would not underestimate is that the type of properties that we need to be calculated and the computational spectroscopies that we need to develop, this is not all there. It's not just doing more of the same. I think we need, I mean, some of the correlations or the interactions that Silke was mentioning, all that is becoming critical if you want to be able to interpret an experiment where by definition the system is typically brought to an excited state. And so all this still requires a lot of theory and a lot of computational development in order to be doable. We are still, I mean, some of the type of development that we have been doing in the past is still badly needed, otherwise we won't be able. And on top of that, people would like to do it and to gain understanding as they measure. So they would like to see our work interacting with the experiment, and not just realizing if there's an outlier in the spectra, some funny behavior, but also trying to get guidance from the simulation. And that means that real time and working on the fly and so on, this is becoming also very important. So all this high performance computing and exascale and all that is also becoming very important in order to be interacting with the experimental work. So that, I think you're right, is one of the aspects where we are going to be really doing something qualitatively different from the past.
So I think Christoph will also.
Just shortly, you said understanding based on simple principles. And I believe that this perhaps is even more core to what we are all doing than reproducibility. That's the core. I want to understand something, and I want to make it understandable in a sense for humans. It must be simple enough. But is it possible that we produce so much data about some cellular mechanisms, and then we have machine learning tools available which allows to do prediction based on the data without understanding? It will be possible. So the question is, how do we react to this? And what exactly is how do we define science in the face of the opportunities coming from that? And this is what humans have to define. This is something that is really at the core of what we should do. Mm-hmm. And this could also be something which should be done in networks like CECAM, because they are international, they are not centered to a certain place, they are open enough, and this should be where it happens.
I couldn't agree more.
Okay. Yeah, Matthias?
So related to what you said, it would be simple, but what if machine learning learns that we already have reached the point where machine learning models are better playing chess, playing Go, at translating from Chinese to English? They may become the point where they get better at doing science. And one question that comes up, how can we understand what they do? And one answer I heard recently if they're better than humans, how can we expect to understand how they think? So the challenge that we face is how can we leverage this, and how is it best used in science, and how will science be changed with those capabilities? That's something to discuss. I don't have an answer, but it's a question I'm posing.
That's a clear challenge. Yeah. So yeah, if there are no more comments, then there is another question. Yes.
I am Marek Cieplak. I'm from Poland, and I appreciate being invited here to give a talk and so on. If you look at the map of CECAM, then it's looking pretty sad. You keep talking about Europe, but all you mean is Western Europe. And but on that map, there's no Portugal, there's no Iceland, there's no Norway, and there's no country east, from of the Eastern Europe. And for instance, in Poland, there's a big. Poland is pretty strong in biophysical simulations and quantum computing, and I'm sure the Czech Republic also has strong electronic structure that is strong, and so on. Now, Poland almost became a CECAM member nearly 4 years ago, thanks to the effort of Professor Tildisley and several people in Poland. But we had misfortune of having a new government. I mean, it was almost signed by the Polish government, by the Minister of Science. Unfortunately, there were new elections, and the new minister did everything to destroy everything that was done or ready to, to be signed by the previous government. And I don't know exactly what are the mechanisms in the other countries, but I suspect that something of a similar nature. So now, and I think it's no good if half of Europe, really population-wise, is not in it. And maybe I understand that the definition of CECAM is state-based, right? That the state has to pay fees and so on. Right, but maybe that should be reconsidered.
I think that one of the important things of CECAM is that really it's a bottom-up organization.
No, I understand that, but still, it was required that a state pays a fee a year later. Not anymore?
No, the members pay the fee, yeah. So
well,
we can't discuss.
Was the bottleneck
we can't
Poland 4 years ago.
I think a bottleneck is obviously is for Poland, but for other organizations. I mean, having to convince administrations and politicians is not easy, and it takes time in some cases. But that's something certainly.
We were required to pay 30,000 of some units. But the only point I was trying to raise here is that maybe one should go by individual membership. Also, right? And so if people from various Eastern European countries and Portugal, could form a unit or something like that, would be, that's all I'm trying to suggest.
That's definitely something to discuss. What are the best ways to circumvent these administrative difficulties to ensure that the scientific individuals and groups can be part of CECAM? So that's also a challenge. Yeah, thank you. So are there other contributions from the audience? Questions to the panelists? No? Yeah?
I'm not really aware of the situation, but it's interesting what is it mentioned. I mean, my aspect will be, CECAM needs support and therefore needs the support from governments. But what about the pressure that may or may not be possible to exert via the European community? Is there any strong relation between the current European community and CECAM?
You mean the European Commission or the European community?
Both.
Well, I mean, I may answer. The European community, as I said, this is really, CECAM is a bottom-up, so in that sense, the European community is definitely involved. And the European Commission, I mean, we as CECAM are involved indirectly because members are involved in projects and are leading. I mean, I think some of the comments of Elisa relating to these exascale challenges, some of those come from the Commission, and we can face them because CECAM actually also helps, or it's a place where some of these initiatives take place, and in some cases, we as CECAM also try to lead. So I think definitely that's something that is changing, what is necessary to be active, and where we keep on trying to play a larger role. And again, I think this is a community effort. So the fact that we have the main players as members of CECAM, I think that's an asset. Yeah. So I had a curiosity in the sense that, I mean, some of the comments that a few of you have made hint into this tension between the importance of software as a facility and algorithmic development versus the existence of these well-developed codes that lead to this kind of push-button attitude that Elisa was referring to. So how do you foresee, for example, related to this infrastructure, to which extent the fact that algorithms need to be developed or are well established, or it creates a difficulty in really moving in that direction, or the other way around? To which extent we should really look, for example, how fast or how algorithms develop to really keep being able to operate and work with them rather than just using them as a black box?
I think it's not, I don't see a contradiction. I think actually the open source type of approach that was mentioned has also made the evolution of the software such that it's very much based on teams who develop, new, for example, the calculation of new properties and the algorithms that are needed for that, and some algorithms become possible just now because the computational power has increased, and that's becoming incorporated in the codes, sometimes in a messy way, and a lot of the work that many of us are pushing is to rationalize the codes in such a way that this strategy, open source strategy of development, doesn't impair the performance. So that, but I think this is not. I wouldn't see the development, the algorithmic work, and the work on the codes as something that is in competition. Actually, it's completely to the contrary. So I wouldn't see. I would see this as a big opportunity, and I see all the efforts coming together over there. Now, okay, let me stop because it's not nice. Somebody else maybe like to add.
I mean, I can add a comment, and maybe the car analogy is good. So you can have a Ferrari and you can have Leclerc. So you can have a tool that is state of the art, and the driver that is state of the art, and that what is a free electron laser, and that what is the software installation that I'm thinking at. And then there is a company that makes Fiat, and hopefully you get people with a driver's license that drive that. But also you can be a 16-year-old, steal the car and drive with that, and you do something, sometimes you crash. I think what I'm thinking when I think at a software installation, I think how we push the state of the art in a systematic way. I think we are actually not pushing enough the state of the art because we don't have the infrastructure comparable to what we are doing for the hardware. And then all of this can percolate. But I wasn't thinking that CECAM should turn itself into a scientific software company. That is very much needed, but it's a different goal. This is how we do the development in interaction with the state-of-the-art experimental facilities.
Mm-hmm. So you would say that lack of systematic approach is really what makes it difficult for these software infrastructures to be established compared to a hardware infrastructure.
I think we have an obvious opportunity that we are not taking. I mean, what is needed costs very little with respect to what we do in all these other fields, but we don't have the funding, we don't have the political awareness, and we don't have the structure within laboratories or university to support that. And to me, it's just a mystery, because I hope that the numbers I showed you make it so obvious that we need it and we are not doing it. And what I'm asking myself, and I keep asking, is why don't we do this? So because somehow we don't take the perspective of sitting on the moon and looking at the Earth. What is happening? We are all sort of thinking very narrowly at our field and what it needs, but the bigger picture often is actually decided by people that don't have the bigger picture.
Yeah, yes.
So related to that, I like what you mentioned about the fiat, because it's often said that we should not write push-button codes because people will misuse them, but we can teach them and educate them, and they can get a license, and then they can also learn to drive the Nega Ferrari, and that's something for CECAM to help do the driving courses for these codes and to help build it, because we only make progress really when people build on things that were done before. We don't always have to rewrite our own code, and I think we have to embrace that. And so I like your idea, and so we should.
If Microsoft wants to donate at 0.1%, we are always happy to take it.
Let's talk over dinner. You already offered to pay for the drinks.
After drinks, in particular.
Yeah, Martin?
I think it's a responsibility of the community to fight for having these resources. Because the resources, as Nicola pointed out, I mean, they are lying around, they are simply used by other people. Because these other people have been there before and have convinced funding agencies or universities that, you know, it's worthwhile putting $1 billion for this and not for that. And for that, the community has to be well organized. I take just one little example. It used to be that at the National Science Foundation, you could get, in Switzerland, you could get reimbursed for all sorts of stuff, mice and, you know, whatever, chemicals, but you could not be reimbursed for computational time, right?
Yeah.
So I spent quite a bit of time explaining at the National Science Foundation that, well, a lot of people do computational science, so we should actually pay for computational time. So you have to change the way money is distributed. It's sort of obvious, but that also means that the community has to give incentives to the people who work on these problems, right? So that my favorite example, you know, I was at Berkeley before coming here. Somebody got in the computer science department got tenure, not based on paper publications, but on a piece of software that had become extremely popular. Okay, but that was very risky of a computer science department to actually say, oh, this person, you know, merits tenure, because the standard is, you know, you need so many papers, so many citations, or whatever. And so it's very important that people that do methods developments, because software is methods, you know, are recognized for the contribution. And if you look at how papers are written, you know, usually the method section is actually not even in the paper. It's somewhere in an appendix, you know, you have to go look up. So the community has to think about this, what in the end matters. I personally think this is extremely important, but, you know, if the community is not in agreement and does not put the right incentives, puts, you know, writes the right reference letters and so on, it's not going to change. But I feel the awareness is here, and, you know, the demand for open source code, reproducible results, and so on is so high that I'm optimistic it will actually happen.
It will happen. To Michele?
I would like to add that there are other communities. I'm thinking of the energy physicists, the astrophysicists, that are well organized the way you say. And I mean, there are lots of people that just do a little photon multiplier, and they do their own career. And we have examples out there. Yep. And the other thing that is typical of this community, that they come together and they move like an army. So yes. They fight at the beginning what they want. Once they decide, it's like a communist thing, you just go for the kill. And we should maybe go in that direction.
Okay. Talking about obtaining resources and funding agencies, maybe one should also come back to one aspect that we have not discussed a lot, namely industrial funding. So the money that Matthias will organize is a good start. Let me ask one question.
Thank you.
So CECAM, as an organization, shouldn't there be immense added value in approaching industries? Are we doing all we could in that way, or is there more to explore in this direction? So that's really a question.
That's also a challenging question. Yeah.
That's a challenge.
Because it's much harder as an individual group to approach industrial companies, obviously.
Yeah.
But CECAM as a collective organism should have better chances there.
Okay.
Can I say, and then I'll shut up.
Yeah, no.
So I love Industry Money for the reason that is actually bringing very relevant problem to us. But I actually don't think that is the role of industry to really support what is a societal investment in this kind of science in the same ways that there are societal investment in other kind of science. There have been the successful model of the public-private partnership, but to be honest, I think CECAM has been also through ECAM, through the Center of Excellence, has had a very visible effort to try and increase really the visibility of the community and facilitate this. But I don't think it's fair to ask an industry should invest in CECAM in doing the science that will be relevant in 20 years. I mean, it should expose a community, and I think it's very precious. When industry comes in, I actually feel much more satisfied when industry gives me money because I know that they are doing it because they need it, rather than I win a grant and because some referee thought that was good. But I think it's really a societal investment. I think what we are doing.
Okay. So I don't know if there is any further final urgent question. Yes.
So I'm a PhD student at EPFL, and I see that a lot of people talk about the importance of method development, but I feel like there's a problem in the model because in a number of times there is not much incentive to work on method development because you might be better off using it, and it can be better for your career in terms of publications because that's how the evaluation is done. And right now with machine learning that has come into our field, there has been more people are doing method development, but I think the incentive there is really so that they have an option that if they leave academia, they can join industry because there is more incentive given by the industry to them. So how do you think this can be solved? Should we really change the model of our research to achieve what has been said?
So I think it resonates and as a personal experience of some of the comments that have been made. I don't know if you have any additional. I think it's really a challenge into how we as a community face this and accommodate the need of these professional careers. Yes, Christoph?
I can come briefly on that. Sure.
So I'm Erik Lindahl, I'm Professor of Biophysics in Stockholm. I'm not sure this is correct, that we don't appreciate things, and I think it's a good example of CECAM too. So this classical workshop in, what was it, in 1976, when a bunch of people sat down and pretty much invented MD. For some reason, people at the time thought that this was not more important than it can be a minor paper in one of the CECAM reports. But in terms of community and everything, this was pretty much important enough to award with a Nobel Prize. So that the whole assumption that it's not being worthy or anything, I think that's wrong. I think maybe the problem is rather with us, that we don't really publish these things. So perhaps one thing that CECAM might be, maybe we should start something at least in electronic form, actually have a CECAM journal or something and start publishing these softwares.
Yeah, I could say probably CECAM as a community will, and the work that is done then is receptive. I think part of the difficulty then is when it comes to the individual or the career as such, and how much then the effort is spent in the development of the codes.
Sure, but I think that we have a currency for this, right? Whether we like it or not, and this currency is grants and it is papers. And I think it's going to be far easier to arrange these careers by actually having the people who do this work publish papers and get grants. Because then we have a system that we will push them in through the departments and everything.
Yeah,
think it's so much an issue of, if I understand what Elisa was saying, it's not so much an issue of publishing, but being recognized as a valuable contribution by the community when it comes to promotion, and not be considered a second tier
second line of There was any additional comment? Yeah.
So I think if you develop a method that really changes a field, then it's not a problem. But that takes time to show the value of it. And so when my group develops new methods, we always try to show the potential. That's one thing. And we always try to also get the codes published. And I have to agree that's a fight, because not because the journals don't like it, but because the reviewer says this is a paper just about the code and it's not suitable for the journal. And then then we appeal, and it does get published because that's not the view of the journals. So but where then the problem becomes more is when those people want to find a job. They are well known in the community, but the hiring committees again have to acknowledge that writing a good piece of code is something valuable. And when it's about like a promotion case as mentioned, then again the people who review that should see that. So as mentioned, it might be us who are the problem here, and we have to just see that this is important for the field.
Okay, so I think that's. I think we have analyzed or bring about a number of interesting and challenging questions. I hope the open discussion has been useful to all of you, and I think we should thank again the panelists for the effort to. Sorry, Martin, you had.
Let me just say one last thing. Yes. It's also about promotion. So. Yes. The fellow who is at the origin of Python, you might know, is actually now a professor of statistics in the stats department at Berkeley. Okay, and he's mostly well known for having developed Python and Python notebooks and so on. So, that's a good sign that it starts to change. People that have very high impact, because it's more about impacts than about, this paper, that journal, I think, at the end of the day. So this can happen. And I take this opportunity to make free advertising, because we have an open science colloquium here at EPFL, where actually Perez, the guy who did Python, will be here, as will be Ingrid Dobschi, as will be Katie Bowman, the lady of the first image of a black hole, etc. So it's a full day on 18th of October. It's free. There will be drinks at the end of the day, and it's all about open science, how science should be advancing by publishing, by being reproducible, by sharing data, and so on. And I think, if members of the CECAM community are interested, I know Nicola will be there, right? If I remember well.
If I'm still invited, I
Very
don't know
good. Okay, you're still invited. Okay.
Yeah.
Anyway, thanks.
Okay, I think it's a good way to finish with a positive example and a good model, because that's something we need. So let's thank again the panelists again. And
so thank you to all panelists. So we now go to the dinner. So remind you that you have to bring the badges to the dinner. Then we'll have about 1 hour to visit the museum, which is of course free. And I think yes, there are some instructions. If you don't have them, there are some instructions on the desk upstairs and a map to go to the Olympic Museum. See you there.
Okay.
Yeah.